This is the final video in the series where I've been using specification-driven development to build an AI assistant that helps a human solve the New York Times connection puzzle. Along the way, I've learned some valuable lessons about what it really takes to make specification-driven approach work, especially when you're working with an AI coding assistant. In this video, I'll wrap things up with an overview of the application after the latest set of changes. I'll walk through the high-level architecture, show how time was actually spent across the different phases and its implications. I'll show working with the AI coding assistant in the context of specification-driven development. At the end, I'll point out the two key lessons I've come away with in this work. The goal of this video is to give you a clear end-to-end picture of what this approach looks like in practice, not just in theory. For the next few minutes, I will demonstrate all the connection puzzle virtual assistant capabilities. In the interest of time, portions of the demonstration will be sped up. Let me show you the connections puzzle virtual assistant and its key features. In this demonstration, you can see the AI assistant working alongside a human to solve the New York Times connection puzzle. The AI's role here is assistive, not authoritative. It suggests patterns and possible groupings, while the human makes the final call. One of the last updates to the application is that the puzzle results are now recorded. After each game, the user can view past puzzles, making it easier to track and learn from previous attempts. So here you'll see game history. We click on that and view past games. And from here you can see I've played two games. One of them I've lost. And here I lost using the Olama Quinn 2.5 LLM, and the other game I was able to win with the OpenAI GPT-5 Mini. Right? So this is viewing previous games. To use the virtual assistant on a new puzzle, there are two ways to initialize the puzzle. You can load it from a file containing the words, or you can initialize it directly from the puzzle image, which mirrors how players actually encounter the game. Here is an example of initializing the puzzle from a file. So we'll go start new game from file, and then we'll choose file, and we're going to look for the puzzle from October the 9th, 2025. First, let's take a quick peek at the file. And you can see here are the words that are in the puzzle: limestone, gorilla photo, figment, fancy, dateline, and so on. Okay? Alright, so now let's set up a puzzle with this file. We select it and click open. And now we'll set it up. And as you can see, we now have the words in limestone, gorilla photo. Alright? So here's an example of where we set up the puzzle from using a file. The other way we can set up a puzzle is from an image. So let's click on that, and for this, I'm recording this. Let's use a live New York Times puzzle. I'm recording this on December the 27th. So here is the puzzle for December the 27th. So let's go see there. Alright, so you can see the puzzle as it appears on the New York Times website. So from here, we're now going to copy and paste the puzzle image. So we're going to copy it. Then we're going to select the paste area within the solver and paste it in. As you can see, we've now copied and pasted the image of the puzzle. And for this, we're now going to ask the virtual assistant to extract the words out of the image using OpenAI GPT-4o LLM. Alright, and if you compare the words on the left with the words on the right, you'll see that the virtual assistant was able to pull out the words exactly from the puzzle image. Okay, so now with the puzzle initialized, now let's start solving it. So we have a couple of options, several options. We can use Olama as a local large language model running locally on my machine, or we can use OpenAI, which for this demo we'll be using that, and we'll be using the GPT-5 mini LLM. Okay, with that specification, we'll now ask the virtual assistant to come up with the first recommendation. Okay, and here we come up with its first recommendation of business economy first and premium, which it says the connections are airline cabin classes. So let's select that, business economy first and premium. And that's correct, airline classes. So I found the yellow group. So I'll now tell the assistant that we found the yellow group. And up here you can see we've updated the counters. We found 1 of 4 correct groups. We've not made a mistake so far. There's 12 words remaining, and that it's recorded our response, the first response. Okay, so now let's continue solving the rest of the, finding the rest of the groups. Okay, looks like we've solved the puzzle. The last one being fairly tricky, uh, with the words being, the last part of the words being alcoholic beverages. All right, so let's tell the assistant we found the purple group. And here you can see we found 4 out of the 4 groups. We made 1 mistake, and you can see the previous guesses here. And now it said we've solved the puzzle, and now let's record the game. Okay, we've successfully recorded the game. So now if we go back to the history and view past games, we now see we have 3 games recorded. The last one being the one that we just played on December the 27th. It was solved, 4 groups were found, 1 mistake. We had a total of 5 guesses, and we're using the OpenAI GPT-5 LLM. All right, so this shows you all the, one last feature is we can export the statistics. So let's do the export. And you can see it extracted the game. We can go to the file, and here we can open it up with numbers. And you can see we now have extracted the data set. All right. All right, this now shows you all the features of the Puzzle Assistant. Thank you very much. Before diving into the details of the specification-driven development workflow, I wanted to share how I use the GitHub Copilot, the AI coding assistant, in this work. While my comments reflect my experiences with GitHub Copilot, I believe these comments will apply to other AI coding assistants. First, Copilot helped with the early specification work. It assisted in drafting the high-level specs that eventually fed into the Spec-kit process. That included generating initial web UI layouts, spotting gaps and inconsistencies, and doing a lot of the tedious document revision work. Copilot also played a big role in driving the Spec-kit workflow itself. It helped translate high-level ideas into more detailed specifications, define the technical plan, and break that plan down into concrete implementation tasks. It also identified inconsistencies and gaps and provide recommendations on how to address these issues. Beyond that, I used Copilot for root cause analysis when things went wrong. When errors showed up, it helped reason through what was happening and suggested possible fixes. It also acted as a sounding board, a way to brainstorm ideas, sanity check approaches, and refine how to tackle the development work beyond writing code. On a more practical level, Copilot answered questions about the existing codebase as it evolved, which allowed me to be more precise as I wrote the high-level specifications. And finally, it generated code. But that wasn't the main event. I saw a lot of value in using GitHub Copilot before and around code generation. Now let's level set on what I mean by specification-driven development. In many code-first workflows, we jump straight into writing code and figure out what we meant along the way. That can work for small changes, but it often leads to rework, misaligned expectations, and AI agents confidently building the wrong thing. Specification-driven development flips that approach. We start by writing clear specifications before any code is written, so system behavior and success criteria are explicit from the start. In this project, I use GitHub's open source project called Spec-kit to do that. Spec-kit provides a structured way to capture intent, plan the work, and drive implementation directly from the specification. That specification becomes the single source of truth. It guides planning, implementation, and verification. This is what makes human-AI collaboration actually work. The spec gives AI agents the context they need, while humans stay in control of intent and direction. So this isn't your father's software development. This is specification-driven, agent-assistant engineering. On this slide, I'm walking through the core Speckit commands and how they fit together in a real workflow. Everything starts with the constitution. This sets up the project's guardrails, the principles, constraints, and assumptions that shouldn't change every time the code changes. Next is specify, where I define what the system should do, behavior, scope, and success criteria before worrying about implementation. From there, plan turns the specification into execution approach, outlining major steps and dependencies. Task then breaks the plan into concrete units of work that can be handled by an AI agent or a human, with each task tracing back to the spec. Finally, implement is where the code gets written, driven by the task, which are driven by the plan, all anchored in this specification. Throughout the process, I stay in control using tools like GitHub Copilot and VS Code to assist with execution, while both the specification and the application code are versioned together in the same Git repository. This slide gives a quick timeline of how the project evolved across phases, so you can see how it grew step by step. In phase 1, the focus was on laying the foundation. I set up the overall project structure, built the initial web UI, and stubbed out both front-end and back-end services. At this point, puzzles were initialized by uploading a file of words, and also put in a basic testing framework in place. Phase 2 is where things started to get interesting. I enhanced the backend to use large language models to generate puzzle solutions. I also added support for multiple LLM providers, specifically OpenAI and Ollama, and updated the web UI so you could switch between them. In phase 3, the scope was more UI focused. I introduced a left-hand navigation sidebar to make the application easier to use and to prepare for additional features. Phase 4 improved how puzzles are initialized. Instead of uploading a file, you can now copy and paste the connections puzzle image directly. A new backend service uses an LLM to extract the puzzle words from the image automatically. Finally, phase 5, which is a recent change, adds persistence. I introduced a local database, backend services to record game results and retrieve past games, and front-end updates so you can view your history and previous results in the UI. Taken together, these phases show a gradual evolution from a simple prototype to an LLM-powered system, and finally to a more complete, stateful application. This slide shows the high-level architecture of the system and how the pieces fit together. I'll walk through it from top to bottom. I'll note that the diagram was created with the help of GitHub Copilot from the actual code base contents, meaning the diagram reflects reality. At the top is the puzzle player, a user in a web browser running on localhost. All interactions start there. The browser talks to the connection solver web app, which is the front end running locally. The front end renders the UI, handles user input, and acts as an API client when it needs data or wants to solve a puzzle. Those requests go over HTTP to the backend service, also running locally. The backend is the central coordinator. It exposes a REST API and contains the application logic. From there, the backend sends out to supporting services. It uses a local SQLite database to persist game results and history, and it calls out to LLM providers for puzzle solving and word extraction, either locally through Ollama or remotely through the OpenAI API. The key point here is that everything is loosely coupled. The front end only talks to the backend, and the backend can switch LLM providers without changing the UI. That separation makes the system easy to experiment with, extend, and evolve while keeping responsibilities cleanly defined. This chart shows how time was spent across each phase of the project, broken into 3 buckets: pre-work, Spec-kit planning, and Spec-kit implementation and verification. Pre-work involves defining the high-level specifications that feed into the formal Spec-kit process. Spec-kit planning includes the /specify, /plan, and /task steps, while Spec-kit implementation and verification are the /implement step plus manual verification by the developer. In phases 1 and 2, very little time was spent on pre-work and upfront planning. As a result, a disproportionate amount of time was shifted into construction and testing, not to add features, but to debug, rework code, and fix behavior caused by incomplete or inconsistent specifications. Starting in phase 3, you can see a clear shift. With better defined specs and more deliberate planning, overall time drops and implementation becomes far more predictable. Phase 4 follows the same pattern. Even with new functionality, implementation and verification stays under control because the intent was clearer going in. Phase 5 increases, which is expected. Adding persistence like a database and game history naturally requires more planning and verification, but the work is still more intentional and less reactive than in earlier phases. The takeaway is simple. Skipping specification work doesn't save time, it just pushes the cost downstream into debugging and verification, where it's far more expensive, especially with AI-generated code. It's not just how much time you spend, it's where you spend it. A bad line of code is usually easy to fix. A bad plan is harder. But a bad assumption or vague specification, that's where things really spiral. On the left, you can see the compounding effect. If research or understanding is off, even good coding effort can still produce the wrong result. You end up writing a lot of code that works, but solves the wrong problem. On the right is the impact hierarchy. The higher you go, research, problem framing, and specifications, the more leverage each decision has. One bad line of spec can turn into hundreds or even thousands of bad lines of code. And with AI-generated code quickly, that amplification happens fast. So the lesson is put human attention where it has the highest leverage. Humans focus on intent, assumptions, and clear specs. Agents turn that clarity into code. That shift, moving effort upstream, is exactly why starting in phase 3, we saw less rework, fewer surprises, and a far more predictable build. The real optimization isn't faster coding, it's better thinking earlier. This slide shows how much code and documentation was generated or modified across each phase. On the left is the approximate lines changed, and on the right is the number of files added or updated. In phase 1 and 2, there's a large spike in code. That's where the core structure and LLM integration were built with relatively little documentation compared to the amount of code being generated. Phase 3 drops off sharply. Changes are smaller and more focused, reflecting a more stable system and clearer intent. In phase 4, documentation increases relative to code. New workflows were added, and that required more explanation and clarification than raw implementation. Phase 5 increases again across both code and documentation. Adding persistence like a database and game history touches more files and benefits from stronger documentation. The key takeaway is that as specifications improve, changes become more intentional, with less churn and better balance between code and documentation. This slide shows the test coverage for both front-end and back-end. The key headline is both are at 80% or higher coverage, which gives a solid baseline of confidence. On the front end, coverage is strongest in the services layer, with integration tests exercising real user flows across component and UI behavior. On the back end, coverage is even more consistent with core services, middleware, and database logic fully exercised by tests. An important point is that these tests were created as part of a test-driven development approach. The tests reflect the expected behavior defined in specifications, not just the implementation details. In an AI-assisted workflow, that matters a lot. When agents generate code, these tests act as a safety net, validating behavior, catching regressions, and keeping the system aligned with the spec as it evolves. The remainder of this video will show you actual interactions with GitHub Copilot in VS Code agent mode in the steps described earlier. In the interest of time, the video is sped up. There will be a voiceover at appropriate points in the video. Before any code was written, I started with pre-work. Using VS Code agent mode, I worked through the high-level ideas in a dialogue with GitHub Copilot using a mix of GPT-4 and GPT-5 mini LLMs. The goal here wasn't perfect detail, it was to clearly capture intent. Once that high-level specification was in place, Copilot helped review and update the Spec-kit constitution to reflect a key change, adding a database. This pre-work sets the guardrails, so when we move into full specification-driven development, both the human and the agent are aligned from the start. This is part of pre-work. We are defining the high-level specifications for the Phase 5 changes of adding a persistence layer with a database and the related web UI changes. Here are the results of the pre-work. This slide shows an excerpt from the high-level specification that will be used as input into the Speckit process. The goal is simple: define what the system should do so that humans and AI agents are aligned before implementation. On the left, we define the UI changes. We add a record game button to the end of game summary. It persists a completed history puzzle to history using a server-side action without changing the rest of the UI. In the sidebar, a new collapsible game history section provides access to past games while keeping the interface clean. On the right, we describe what data must be persisted in the database and what is shown for view past games. We define an option to export CSV, the persisted data. Finally, the high-level specs define the new functional behavior expected to ensure session data records those LLM details at the right time without affecting existing behavior. Next comes Speck-kit planning, where we flesh out those high-level ideas. Using the specify command, I decompose the original spec into detailed user stories and functional requirements. Once the detail was in place, I ran /clarify to surface gaps, ambiguities, and missing requirements. This step is critical. It's where fuzzy thinking gets exposed before any code is written. By the end of this stage, the intent is explicit, testable, and ready to drive the rest of the workflow. All right, we're now using Speck-kit slash specify command to translate the high-level specifications into detailed user stories, acceptance criteria, and functional requirements. Once those detailed requirements were defined, I'm now reviewing this to make sure the high-level specifications were translated correctly into these detailed specifications. I'm now committing the detailed specifications into the Git repository. I'm now running the /clarify command to determine if there are any gaps or inconsistencies in the detailed specifications. You may have noticed that for any gaps or inconsistencies found, GitHub Copilot are making recommendations on how to address those. This slide shows the outcome in specification-driven development. That high-level intent gets translated into detailed user stories, requirements, and acceptance criteria. What is shown is only a subset of the detailed specifications. On the left, we break the feature down into concrete user scenarios. These are written from the user's point of view and describe exactly how someone records a completed game or reviews their game history. Each scenario includes clear acceptance criteria written in a way that's directly testable. That's important because these criteria don't just document behavior, they define what done actually means. On the right, the same intent is expressed as explicit system requirements. These cover the UI, session management, backend persistence, and recommendation tracking, all tied back to the original goals from the high-level spec. The key point is that nothing new is being invented here. This is a systematic translation of the earlier high-level specification into precise, unambiguous instructions that an agent or a human can confidently implement. From this point forward, everything in the Speckit flows from these artifacts. They drive planning, implementation, testing, and reveal exactly where verifications are needed. This is the handoff moment. Once you have this level of clarity, the rest of the development process becomes far more predictable. With the detailed specifications in place, the next step is creating the technical plan. Using the /plan command, I translated those requirements into a concrete implementation approach. The key point here was the high-level technical requirement for adding a database. What needs to exist, how it fits into the architecture, and how it should be tested. By the end of this step, we're no longer talking about abstractions. We have a clear executable blueprint that both humans and AI agents can follow. I'm now using Speck-kit's /plan command to generate the detailed technical plan for the project. After the technical plan was generated, I reviewed it, and as I was reviewing it, I noticed there were several things I wanted to change. So here I'm directing GitHub Copilot to make those changes to meet what I want as far as the phase 5 changes. After GitHub Copilot makes the requested changes to the technical plan, I now commit the technical plan to the Git repository. This slide shows an excerpt of the technical plan derived directly from the detailed specification. What you're seeing here is only a subset of the full plan. The complete technical plan is much larger, but this excerpt shows how requirements get translated into concrete engineering decisions. On the left, we validate the plan against core principles like API first design, test first development, and type safety. On the right, those requirements are mapped into real project structure: documentation, backend services, front-end components, database changes, and tests. At this point, the spec is no longer abstract. It's a clear, traceable blueprint that both humans and agents can execute against. This is where Speckit turns intent into implementation. With the technical plan in place, the next step is creating the task list. I use Speckit/task command to generate a detailed ordered set of implementation tasks. Then I ran /analyze to validate those tasks against the requirements and the technical plan and to surface any gaps. The result is a task list that's explicit, traceable, and ready to execute, so both humans and AI agents know exactly what to do and in what order. The /task command now generates the detailed task list to implement the phase 5 changes. After the task list is generated, I'm reviewing it to make sure the agent generated a complete task list. Once I'm happy with the task list, I now commit it to the Git repository. I'm now using the /analyze command to ensure that the generated task list is consistent with the functional requirements and the technical plan. If there are any issues, GitHub Copilot helps me address those issues with recommendations. After resolving any identified issues, I commit the updated task list to the Git repo. This slide shows an excerpt of that task list. It's only a subset. The full list is much larger, but it captures how the work is structured. The tasks are deliberately ordered. We start with environment and infrastructure setup, then move to foundational pieces like database schemas and core models, and only after that do we implement user stories. This prevents common mistakes like trying to use a database before it exists. As the plan progresses, tasks map cleanly into backend and front-end work for each user story. You also see defined checkpoints where the developer is expected to pause and manually verify behavior before continuing. The result is a task plan that's executable, traceable, and designed for safe incremental progress. Exactly what specification-driven development is meant to enable. Once planning is complete, we move into construction and verification. I use the /implement command to generate the code changes needed to satisfy the detailed specifications. But this isn't a hands-off step. At the specified checkpoints in the task list, I manually verify the behavior in the running application to make sure it matches the spec. This human-in-the-loop verification is critical. It's how we keep AI-generated code aligned with intent and catch issues before they move downstream. Finally, this is the part of the process where we are generating code with the /implement command. In real time, this part of the process took just under 2 hours. You'll see alternating images of GitHub Copilot generating code and me manually verifying the generated code. The points for the manual verification are called out in the detailed task list as checkpoints. This sped up version of the video will take about another 5 minutes. I'll come back on after this segment. From the video, we saw GitHub Copilot actively generating code based on the detailed specifications, technical plan, and task list we created earlier. This isn't free-form coding, it's guided execution against a well-defined spec. On the right side is the other half of the equation, verification. Here is an example of me validating behavior of the running application to confirm that the implementation matches the specification. This human in the loop is critical. Even with strong specs, agent can make mistakes, and verification ensures the system behaves exactly as intended. Construction and verification work together as a tight loop. Code is generated, tested, reviewed, and validated before moving on. This is where the earlier Spec-kit work pays off. Implementation becomes faster, safer, and far more predictable with clear checkpoints for human oversight. If you take away just two things from this video, let them be these. First, AI coding assistants do far more than just generate code. They help write and refine high-level specifications, spot gaps and inconsistencies, recommend fixes, translate ideas into detailed requirements and plans, analyze errors, and even handle a lot of the tedious document revision work. Code generation is important, but it's only one small piece of the value. Second, this changes where human developers' time go. Instead of spending most of our time hacking on code, our effort shifts to the highest leverage work, defining clear specifications, reviewing and validating what the AI produces, and verifying that the system actually does what we intended. That shift from typing code to shaping intent and verifying outcome is the real impact of AI-assisted development. If this way of thinking about AI-assisted development was useful, give the video a like, subscribe to the channel, and I'll see you in the next one.